So we're fortunate today to have Dr. Nushin Estakri from Chapman University. And Professor Estakri will take us through an overview of quantum, I think so that we can all get level set, a little bit about the ecosystem, and hopefully you'll sort of come out of here appreciating all that's involved with quantum, where it's going, and the fact that it's past just theoretical qubit just definitions. And she's also doing some interesting research, so I think you'll be sharing that as well. So with that, without further ado, Dr. Nushin Estakri.
Thank you for your time, for joining us today for my talk. It's great to be here, and thank you for the kind invitation to the Orange County ACM chapter meeting. Today I'm going to tell you about the quantum world, past, present, and future. This is the outline for our meeting. We're going to talk about some backgrounds. There's the emergence of the quantum physics, as well as some of the basic concepts of the quantum information science. Then I'm going to tell you about the landscape of quantum technologies, specifically the modern quantum computing architecture, as well as the quantum technologies ecosystem. And after that, I'm going to tell you about the quantum research in my group. We work on gate-defined quantum dot spin systems, as well as quantum light and its interaction with disordered media. So first things first, let's talk about some background, the emergence of the quantum physics. Physics is basically, at its course, trying to uncover the principles that describe what's happening in the world around us and how the physical world works. And up until the late 19th century, there has been a lot of great development and a lot of advancement in different categories, in fundamental categories that are pillars of classical physics, such as Newtonian mechanics, thermodynamics, statistical mechanics, electromagnetism. But at the early 20th century, there were some experiments and theoretical discoveries and advances that showed that the classical physics cannot really explain all natural phenomena. There were some observations, some experiments that could not be explained by the classical physics. And that started the emergence of the quantum physics. I'm going to tell you about some of those observations and how it led to the development of the quantum mechanics. One of the most famous ones is about the understanding of structure of atom. In the 19th century, it was proposed that atoms are actually hard spheres that cannot be subdivided. But later on, electron was discovered with a negative charge. And in the 20th century, there was experiments, gold foil experiment, that showed that basically looking at the scattering, it showed that besides the electron, there are also positive charge sitting at the core and has a lot of mass as well. So that contradicted with classical physics because electron has negative charge, it's moving around a positive charge, constantly loses energy, and it would fall into the core. So that did not match with the understanding of classical physics. There was also blackbody radiation, specifically the emission spectra of the blackbody radiation, such as the one that's shown in this graph here. It has a huge contradiction with the classical physics. We call it ultra-fast catastrophe because classical physics predicted that at shorter wavelengths, the emission should be higher. It should not drop. But that was not something that the experiment was giving. And the shape of the blackbody spectrum was not able to be described by the classical physics. That's when Max Planck came in, looked at the experimental data, and introduced the concept of quantized energy. The energy cannot be divided after a certain point. The units of energy. And that helped solve the ultraviolet catastrophe. Other examples in terms of shortcomings of classical physics in the early 20th century was the photoelectric effect. Then when the light interacts with matter, it was predicted by the classical physics that depending on the intensity of the light and duration of the light, it would always be the case that the electrons would leave the matter, would get released from the matter. But that was not the case, and it was already observed by Hertz in the 19th century. That phenomena, Einstein was able to actually find a solution for that and propose a solution for that, and that's through the fact that the light is quantized, and we call the quanta of light photons. The light that was considered for a very long time to be only wave, it was very much understood as being the wave in electromagnetism, was now understood through the proposal and solution of Einstein that it's actually also acting like a particle in this experiment. And it matched with the experimental observations. So in the experiment, they were seeing that it does not, it depends on the frequency of the light that's actually heating the matter. Below certain frequencies, this was not happening. The electron would not leave the matter. And also the velocity of the electron would depend on the frequency. So it was not matched with the classical physics, but with the idea of having a quantized packets of light, which we call photon, that Einstein discussed, we're able to explain this phenomena, photoelectric effect. And after that, de Broglie mentioned that, light that we knew was a wave is actually showing properties of particle. Why not particles show properties of wave? And one of the particles that we know about is electron. Electron has been known to be a particle showing properties of a particle for a long time. So the hypothesis is that the electron would also show properties of wave. And that was shown through the electron diffraction experiment. This shows the diffraction of the electron, and you can see constructive, destructive interference. It's showing the behavior of wave, even though it was understood to be a particle. Same thing for the double slit experiment, which was done for wave, for light. When it was conducted with the electron, we're able to see the constructive and destructive interference pattern for the position of the electron in the detection plane as it passes through double slit. So that started the discussion that today we call it wave-particle duality. Electron behaves like a wave, behaves like a particle, as well as the photon that behaves like a wave and behaves like a particle. So we call this wave-particle duality that de Broglie was talking about. So these are just some examples of the shortcomings of classical physics, which helped the scientists Einstein, Planck, Dirac, Heisenberg, Schrödinger, and other brilliant scientists to actually come up with the solutions which build the foundations for having a quantum mechanics. Quantum mechanics is a framework, it's a fundamental framework for describing what's happening in the nature, and actually helped remove these limitations that the classical physics was having. It has some fundamental postulates, for example, on the Hilbert space, on the state vector of a system. When we have composite systems, how does the state space look like? When we have quantum measurement, quantum operation or quantum evolution, how does that look like? So we have certain postulates in the quantum mechanics that builds a whole framework for understanding what is happening in nature. For example, we know that one of the postulates that the continuous time evolution of a closed quantum system is described by Schrödinger equation. Similar to the classical physics, in the quantum mechanics and quantum information in general, we can talk about bits of the information. The units of the quantum information are called a qubit. A qubit is a quantum bit, a unit of a quantum information. And if I have one qubit, I can represent it by a complex vector. In terms of math, that corresponds to a complex vector. For example, this is one qubit. It's a vector with two entries, alpha and beta, that are complex numbers. So it lives in a complex vector space. The dimensionality is 2. We always have it with unit norm. That's how we define a qubit, the unit of a quantum information. And there are some favored choices. For example, if we pick 1, 0, we call it ket 0. That's called 0 state. We pick 0, 1, and we call it ket 1. That's 1 state. Those are some favored choices. This is called computational basis state for representation of a qubit. I could have very well chosen a different basis for representing a qubit, such as ket plus, ket minus. That's in the form of a superposition between ket 0 and ket 1. But at the end of the day, in terms of a math, a qubit is represented by a complex vector. Talking about another postulate of quantum mechanics, which is about a quantum evolution, It says that the evolution of a closed quantum system is described by unitary transformations. So mathematical unitary operations describe how a quantum system evolves a certain amount of time if it's a closed quantum system. So starting with a state of a system at time 0, we call it ket psi, which is a unit vector. After some time, through some evolutions, this evolution can be in the whole quantum computing process, the whole algorithm inside the chip, as long as it is unitary. At the end of that operation, the state of the system would be another unit vector, ket phi. So mathematically, this is a unitary transformation. Now this gives us the possibility to use quantum evolution, one of the postulates of quantum mechanics, to have quantum operations that are interesting for computing. We would be able to build quantum gates out of these quantum evolutions. These are some example gates, which are called quantum logic gates. It can apply on 1 qubit or more than 1 qubit, 1 qubit, 2 qubit, or 3 qubit. Let's say if I have a gate, a quantum logic gate that applies on 1 qubit. So the famous examples are these gates, poly X, Y, Z gate. These are poly operators that they change the state of 1 qubit. And also the last one is identity. It doesn't change any state, but for the completeness. One other famous example besides the poly gates, which have certain properties, is the Hadamard gate with this 2 by 2 matrix representation. For example, looking at the poly X gate, what it does, if I have a qubit at a state ket 0 and I apply a poly X gate, the state would be ket 1. So it changes ket 0 to ket 1. And if I apply another poly X gate, it changes ket 1 to ket 0. Hadamard gate is actually very interesting because this is the gate that it can build superposition for us. If I apply a Hadamard gate on my quantum computer to a ket 0 state, then I get a ket plus, which is an equal superposition, symmetric superposition between ket 0 and ket 1. And if I apply it on ket 1, I get ket minus. Similar superposition, but with a different phase. And there are more single qubit gates. So in any quantum hardware, one of the objectives is to be able to actually implement these gates with a very high fidelity. Other group of gates are, for example, multi-qubit gates, such as 2 qubit gates. 1 qubit, Alice has 1 qubit, Bob has another qubit. Then apply a gate between those 2 qubits. One example is C0, control NOT gate, CZ gate, control Z gate, or swap gate, or other examples. For example, here in this slide, I have control NOT gate. One of the qubits is control, the other one is target. And depending on the state of the control, then the target would either receive a poly X gate or it would be left unaltered. For example, if I apply a C0 gate to 1, 0, it changes it to 1, 1, ket 1, 1. And these are the transformations for the computational basis state because they can actually represent all the possible states for 1 qubit in the Hilbert space of 1 qubit. Speaking of qubits, the qubits can be represented by points on a unit 3-dimensional sphere, which we call it block sphere. Every single qubit state that we have, just 1 qubit, correspond to 1 point on a unit sphere. There's a 1-to-1 map. Every possible point on the sphere is also one state of 1 qubit. This is a very important and useful visual tool because it helps designing the quantum evolutions and quantum operations. If the qubit starts at 1 point on a sphere and the operation would actually move it to another point on a sphere, it would be able to actually track that trajectory, design that, and be able to get very good fidelity single qubit gates using the visualization. The visualization certainly helps. That's for the 1 qubit. For the 1 qubit talked about, we need 2 basis states, 2 computational basis states, ket 0 and ket 1. If we have 2 qubits, then I would need 4 computational basis states, ket 0, 0, ket 0, 1, ket 1, 0, ket 1, 1. And every possible state, quantum state, in that Hilbert space can be represented using this basis state with the coefficient, with complex coefficients. Now, if I have 3 qubits, I would have, you might be able to guess that I would need to have 8 basis states to fully represent a 3-qubit system. And the coefficients in the superposition of these basis states, the coefficients of those terms would determine the state of a 3-qubit system. If I extend it to n qubits, I would need 2 to the power n computational basis state, or any basis state, to represent an n-qubit system. Now we start to see a big difference between the left-hand side and the right-hand side. One is exponentially larger than the other one. And that's where the classical computers have a very hard time simulating what the job of a quantum computer. Quantum computers become extremely difficult to get simulated with a classical computer because of this difference. To give you an idea, to give you an example, if I just want to store, don't do any operation, just store the quantum state of a system that has 46 qubits, that corresponds to a RAM size of 1 PB. 1 PB is 2 to the power 50, just for storing the state of 46 qubits. Now, quantum computers, you can see the struggles to efficiently simulate quantum systems. Classical computers struggle to efficiently simulate quantum systems. We cannot have a lot more transistors on the classical computers to immediately increase the computation power. We originally had that option. Basically, a long time ago, every 18 months, the number of the transistors in the IC would get doubled, which was corresponding to the exponential increase. But after some time, the transistors got very small and small that we actually cannot do that any further. That's the point that Feynman introduced the idea of using a quantum computer to efficiently simulate quantum systems. So if you want to do some quantum computation, if you want to simulate a quantum system, why not use a quantum computer or another quantum system to simulate that? That's called the idea of digital quantum simulation. So for example, if I have a system that I want to simulate, it's a molecular interaction, it's a chemical reaction. If it's a very complex chemical compound, that's basically, mathematically on paper, it has a lot of qubits to represent. It's a very complex, high-dimensional irreducible space that we need to simulate. Feynman's solution is to actually emulate that system on a quantum simulator, on another quantum system. And by emulating that means prepare the qubits, prepare the gates that would actually represent the quantum evolution that happens in the system that you want to simulate, and simulate that on the quantum computer. And for that, there are, for example, here I have the chip from IBM, but it doesn't have to be superconducting qubits. There are so many different platforms can be used as a quantum simulator to study the problems in condensed matter physics. For example, superconducting qubits can be used, trapped ions, neutral atoms, quantum dot spin can be used, photons can be used for that, and we're going to talk about that shortly. Now that we talked about Feynman's idea of having a digital quantum simulation, we're talking about using quantum computers for computation, so we need to compare that with the classical computation, the one that we are used to. In the classical computation, we have classical bits. What are the properties of classical bits versus the quantum bits or qubits? If I have a classical bit in all of our computers, then the space would be 0, 1. So the state would belong to 0, 1. It would be either 0 or 1. And if I generate a random bit of classical data, then it would show 0, 1, 0, 1 with a 50-50% chance probability for each of those. But what about a qubit? A qubit would belong to a vector space. I would need two basis states, such as ket0, ket1, or ket plus, ket minus, to describe an arbitrary state for that. Most importantly, it can live in a superposition with complex amplitudes to describe that. So this is a superposition between ket0 and ket1 computational basis states with complex coefficients alpha and beta that shows the state of an arbitrary qubit. That's a perfect superposition. And the amplitude of those coefficients to the power 2 shows the probability if I do the measurement to find it to be in state 0 or state 1. For example, if I have 1 over square root of 2 ket 0 minus I ket 1, that's a perfect superposition. And if I do a measurement in the computational basis, I will get 50% of the time ket 0 or 0 in the output, and 50% of the time I get ket 1. How can I build it in real world? What would be that ket 0, ket 1? It can be, for example, the spin of electron. So spin of the electron, the eigenstates of the spin 1/2 operator would be spin up, spin down. So that would be an equal superposition between the spin up and the spin down for the electron. Now this is about the units of computation, qubits. How about operations? The operations are done through quantum circuits. Quantum circuits are when we bring in quantum gates, different quantum gates, single qubit, 2-qubit gates with some initial state together and apply a computational model. This is a step-by-step process. For example, this is a sample quantum circuit. This is a teleportation circuit. This is a quantum teleportation circuit. Let me walk you through that. So this is for the case that Alice and Bob are actually this is for the case that Alice wants to teleport 1 qubit to Bob. So Alice is sending 1 qubit to Bob through quantum teleportation. So no actual qubit is being sent, but the qubit is teleported from Alice's side to Bob's side. It disappears on Alice's side and reappears on Bob's side. This is a quantum circuit for that teleportation process. Initially, this indices A and B correspond to Alice and Bob. Alice and Bob have a state that's maximally entangled. I'm going to tell you how it's generated. Ket 5 plus, that's a maximally entangled state. And Alice has 1 extra qubit with the letter C showing that. She wants to send that to Bob. Okay. And for doing that, she applies a C0 gate with a Hadamard gate. She does the measurements and communicate that through the classical channel to Bob. Based on the data that Bob receives, he applies 2 gates to the qubit that he has. And the qubit that Alice wanted to teleport would appear on Bob's side. So this is one sample circuit that does the quantum teleportation. Unlike classical circuits, you immediately see that there are differences in quantum circuits, something that is not present in classical circuits. Superposition, entanglement, interference, all of these properties that are used in different quantum circuits, they do not have a counterpart in classical logic circuits, digital logic circuits that we use for classical computing. For example, if I use a combination of Hadamard gate and control not or C0 gate, and I apply that to ket 0 in the output, I get the maximally entangled state ket 5 plus. We call this Bell state generator because depending on the input that you give, there's 4 possible cases, 0, 0, 0, 1, 1, 0, and 1, 1. You would receive in the output maximally entangled state that are called Bell pair or EPR pair. For example, ket 5 plus is 1 over square root of 2 ket 0, 0 plus ket 1, 1. So this is maximally entangled between the 2 persons, Alice and Bob. And that's something that they can use to have quantum teleportation. Important applications are quantum algorithms. Quantum algorithms uses these features that we talk about, superposition, entanglement, and so on, to have faster or more efficient solutions compared to classical algorithms. Examples, famous examples are Deutsch's algorithm, Deutsch-Jozsa, Shor's algorithm, Grover's search algorithm for searching on a structured database. And one thing that's common among these most of these quantum algorithms is what we call quantum parallelism. This is a fundamental feature to the quantum mechanics, and it shows up in many quantum algorithms, which makes it very much different from parallel computing in classical computing. In the quantum parallelism, at the fundamental level, if you want to evaluate a function, let's say function f, with the input A, we want to evaluate f of A. Through the quantum parallelism, the quantum computer evaluates the function for many different inputs at the same time, simultaneously. So this is different from classical parallel computing, that different circuits that are copies of each other are generated, and each of those are evaluated at the same time. So this is very much, this is something that's done in a supercomputer, such as the one from the IBM that I'm showing here. But in the quantum parallelism, the circuit is just generated once, and it's evaluated once. There's only a single query, for example, to the oracle. So it's fundamentally different from parallel processing or parallel computing. And this is a circuit for the Deutsch algorithm for finding if a function is balanced or constant, that with only a single query or single evaluation of that function would be able to say if it is balanced or fixed, as opposed to the classical computing that would need to evaluate that function 2 times. So these are the big elements, the big components of the quantum information science. Talk about quantum algorithms, quantum circuits, the units of quantum information, all those fundamentals. That helps us to talk about the current landscape of quantum technologies. We're going to talk about modern quantum computing architecture. What do we want from a modern quantum computing architecture? It should be able to represent qubits, hopefully a lot of qubits. It needs to be initialized. Should be able to apply different operations, different gates, and should be able to measure the state of those qubits with a very high fidelity. Everything needs to be done with a very high fidelity. So we would have a very high performance quantum computing. Important physical criteria are scalability, being able to have a lot of qubits with a long coherence time. We do not want this to decohere. The gate fidelities, measurement fidelities, state preparation fidelities, all of these should be very high and should have a very good connectivity. But how can we build such a quantum computing architecture? What are the strategies? How can we build a qubit? There are 2 different ways to build a qubit. The first one is by controlling and measuring quantum particles, such as electrons or photons, something that nature gives us. Use something that's already available in nature, such as an electron or a photon, to build a qubit. Those are called natural qubits. We can also use atoms, molecules, ions. And the other technique is through synthetic qubits. Synthetic qubits are constructed, engineered devices that exhibit the quantum behavior, such as superconducting qubits, transmons, fluxoniums. All of that are synthetic qubits. Those are engineered devices. Let's see some examples from these modern technologies. The first group are superconducting qubits, which are synthetic qubits. They use Josephson junction. They're used by many companies, like Google, IBM, Rigetti, for having a quantum computer. They need to be cooled down, so they are cryogenic operation. They have a very fast gate operation. Because they need to be cooled down, they're always limited by electrical wiring. And they have a large physical footprint. The next category are semiconductor-based quantum dot spin qubits. These are gate-defined quantum dots. These are CMOS compatible, which is a bonus because that means that it can be scaled. So this industrial scalability is a positive factor here. They are compact qubit compared to the superconducting qubit. They also need to be cooled down to cryogenic temperature. So that's a challenge, which means that they're also limited by electrical wiring. And they are also used in different academic labs and part of the industry. The next group are trapped ion qubits. So ions are trapped inside, for example, a Paul trap here, or a 2D surface version of that. This is on the right-hand side. That's from Quantonium, 2026, this year publication, that this is a 2D surface trap for trapping ions so that they can be manipulated and quantum operations can be applied with a very high performance. They need stable laser sources to manipulate the qubit. They have a long coherence time, but the gates are also slow. These qubits have very high gate fidelity, very, very high gate fidelity, and they have all-to-all connectivity, which is a very positive thing. They communicate with each other through vibrational modes of the system. Quantonium IonQ are focused on building these modern quantum computing systems. For example, this is from ytterbium. Ytterbium can be used as an ion. The next category are neutral atom qubits. For example, the rubidium. They need optical tweezers. They have a long coherence time. They have flexible qubit connectivity. But they also laser-based control, which makes it a very complex optical setup. This is a programmable two-dimensional array of Rydberg atoms for qubits. So the optical setup is very complex, and there's always a chance to lose the atom from the trap, which means losing a qubit. So there are challenges, but there are also positive points about neutral atoms as well. So you can see that all of these platforms, they have advantages and disadvantages. And the last group that I want to talk to you about are photonic qubits, that they use photons to encode a qubit, such as polarization of a photon, a fundamental property of a photon, to encode a qubit. These systems have a big advantage that they can be operated at room temperature because they have high thermal decoherence immunity. It does not need to be cooled down, the system itself. Another big advantage is that they are compatible with the communication infrastructure that we have, which is fiber optics. The challenge is that the photon can get lost, the efficiency of the detectors need to be improved, the efficiency of the single photon generation needs to be improved. The entangling gates are difficult to implement. They need a very high quality sources and low loss optics. For example, this is a system from PsiQuantum, and this one on the bottom is actually a photonic quantum computing chip from Xanadu. There are other platforms too, but I tried to mention the big competing platforms as much as I could. I tried to cover as much as I could. Now, these are the modern architectures. We'll talk a lot about the hardware, what it looks like. But what about the quantum technology ecosystem? The ecosystem needs to be able to actually address real-world applications, and it needs to be practical. It's not just about the hardware. We're talking about the need for a comprehensive layered ecosystem of technologies, services, infrastructure, including a high-performance software stack. It's not just about a qubit, it's not just about the hardware. The software and the combination of these two platforms being able to operate at the same time is also very important. For example, this is a system view of a quantum information processor from IBM that shows that the physical quantum processor is important. The qubits are, the physical qubits are actually at the bottom of this stack. They need to be controlled. They need to be able to do the measurement on that. And quantum error correction needs to be applied because qubits are very susceptible to noise. But also, it means that it needs to be controlled at the logical layer. So combining multiple physical qubits to build the logical qubits, we need to be able to implement structure to control the logical qubit at the logical qubit layer. The controls that are applied to the logical qubits, as well as the measurements and as well as the quantum algorithm, which is the abstract part sitting at the top of this stack. This is another visualization from QTech that shows that, okay, when you think about it in terms of the different layers, the quantum algorithm is the abstract application. It's at the very top layer. We have an idea, we have a mathematical framework that we want to implement. It's really abstract, sitting at a very top level. But it needs to be translated all the way to the bottom layer where the qubits are sitting. So it goes through multiple layers, the programming paradigm, the different programming frameworks or software development kits, quantum arithmetic, runtime, the compiler, the quantum version of the compiler needs to be present. ISA, instruction set architecture, also needs to have a quantum version that's fully developed to actually be an intermediate layer between what we want to achieve in terms of the gates, in terms of the optimization, and in terms of minimizing the gate time and everything, and what is really happening at the hardware. And it needs a microarchitecture to translate that to what's happening on the hardware, and eventually all the controls and all the controls are classical. We apply voltages, we apply magnetic field, so this needs to be translated to the classical controls very close to the quantum chip as well. And this is IBM quantum roadmap. I know that it's a bit small, so I'm going to highlight the important parts. You can see that on the IBM website. So the point of this slide is that you're focusing both on the hardware and the software and what goes in between. So it's a full ecosystem of technologies that needs to be developed, and you would be able to see what are the objectives and how much it has been achieved. So for example, at the bottom, you would be able, in the section when they report the hardware, you can see the number of the qubits that's their objective to achieve. But in the other sections, like they talk about the algorithms. They talk about discovering different algorithms. They talk about applying different algorithms to the cases that are relevant to the immediate applications based on the needs of the user. They also talk about orchestrating workload for quantum plus HPC. So they introduced using the language C to actually, with the software development kit, so that it would be able to integrate more easily with the HPC. They also talk about the possibility of having workflow acceleration and how it's important to actually combine the classical optimization with the quantum optimization at the same time, because no quantum algorithm everything is purely quantum mechanical in there. There are so many subroutines that are classical, and it needs to be computed using the classical computation technique. But it needs to be done at the same time that the quantum part is implemented. So being able to actually have those at the same time is important, such as verifying, monitoring the workload, trying to optimize that based on this intermediate layer between the abstract version and the hardware layer. Okay. And quantum technologies are beginning to think about real-world problems. We're just starting to think about real-world problems, such as problems in finance, risk modeling, portfolio optimization, in pharmaceutical, drug discovery, molecular simulations, artificial intelligence and machine learning with a quantum machine learning, as well as the logistic and supply chain for routing, allocation, and material science, always development of the new materials. So these are some very important real-world problems that quantum technologies are beginning to think about contributing to. With the technologies that we have, we are currently looking at hybrid setups. Hybrid setups are setups that classical systems are working alongside the quantum processors. We have already developed the classical computing to a very good extent, so there is no reason to set it aside and start working only with the quantum computation. So the hybrid setup is very important so that the classical systems can be used in combination with the quantum processors to find the solution for advanced complex problems, such as VQE, variational quantum eigensolver. This is a quantum algorithm that's hybrid. So some part is done in the quantum processor, but the optimization is done in the classical computer. And it's used in different applications in chemistry, finding a ground state of a molecule, for example. And qubits are always very susceptible to noise in different platforms, all the platforms. If it's a semiconductor, superconductor, all of these are very susceptible to noise. So one other part of the current quantum technology ecosystem, the last part I want to talk about, is actually the quantum error correction. The qubits are not perfect. They are very susceptible to noise, so we should be able to actually correct for the errors that happen. This is fundamentally different from what we have in the classical computation. There are some similarities. I'm not saying that they are 100% different, but the techniques that are developed for the quantum error correction, there are so many different techniques. For example, surface codes. This is one example of a surface code for encoding one logical qubit using 101 physical qubits. This is one that Google used in the recent publication that they mentioned they have a quantum error correction below the surface code threshold. So this is the distance 7 surface code for generating one logical qubit that is robust to noise using a lot of qubits, in this case more than 100 qubits that are physical qubits. Quantum error correction is essential so that we would be able to detect the errors and we would be able to remove those errors at the large-scale quantum system. The objective, the ultimate objective, is to have fault-tolerant quantum computing, but before we get there, we should be able to actually very efficiently detect the errors and correct for them through different codes such as surface code. And with that, we talked about the basic areas that are covered in the quantum technology ecosystem these days. Okay, in the next section, I'm going to tell you about the quantum research in my group. So I'm going to tell you about two platforms and two research directions that we work on. The first one is the gate-defined quantum dot spin system. So I'm going to start with this system. Quantum dots are actually one of the most promising platforms for large-scale quantum computing because it's CMOS compatible, has very good fidelities as well. They have been shown with different applications, such as the quantum error correction, running a 6-qubit quantum circuit, but the number of qubits is still not very high. There are challenges with that. And one solution for this is to actually use modular structures and architectures. Using a quantum bus, which is a quantum version of a bus that we have in classical computing. Use a quantum bus, for example, with a superconducting resonator, to connect different modules. In each module, we would have a certain number of qubits that we can very efficiently manage. And through this process, we would have a quantum processor with a lot more qubits. For this research project, our goal is to actually theoretically investigate short-range and long-range entangling operations, the operations that are within one module and operations that are across two different modules that are entangling operations, because those are very important for quantum computing. This is our system. It is a 3-qubit quantum dot system. This is a superconducting resonator at the center. One unit is a 3 quantum dot system with 2 electrons. And the other system is a double quantum dot system with 1 electron trapped inside. The electron is delocalized across the double quantum dot and the first 2 quantum dots of a 3 quantum dot system. And 1 electron is confined to the 3rd quantum dot. So basically, this is a 3-qubit system. And this is a cross-section of that system. It's a silicon-silicon germanium heterostructure with those electrons trapped inside. It's capacitively coupled to the resonator, and we'd be able to control with the gates the operation of those qubits. I'm going to skip the mathematical details. I encourage you to read that through our publication in 2024 explaining these systems. It actually became an editor's suggestion at that time. And I'm going to skip the mathematical details, and we're able to drive an effective Hamiltonian for this system using mathematical techniques, and it shows different terms. It shows the qubit transition frequencies for the 3 qubits that we have, long-distance resonator-mediated coupling, that's something we are going to use for having entanglement between modules, as well as short-distance exchange coupling. We're going to use that to implement entanglement within a module in the processor, as well as some residual short-distance coupling from the spin-charge hybridization. So this is very small, the last term. In the next step, we actually tested this effective model against the Hamiltonian for the entire system before we find the effective model. And we can see that this effective model that we found actually accurately captures the behavior of the low-energy spin qubits. The transition frequencies, as well as the resonator-mediated and exchange coupling strength are very much matched with what I found in the effective model. This gives us a lot of power to use that effective model to design entangling operations. So the first step was done. In the next step, we used that effective model and designed entangling operations. We designed two sets of operations, one within one module, which is a triple quantum dot module. We implemented fast adiabatic CZ gates. These are maximally entangling gates. We used energy spectral density engineering, it's a signal processing technique, to find the profile of the voltage that needs to be applied to the tunnel barrier between those quantum dots to implement the gate. So this is the pulse that needs to be applied to the tunneling coefficient, and we can see that the CZ gate fidelity versus the time for these quantum processors are actually very, very high. The gate fidelity is more than 99.98%. And the gate time is around 100 nanoseconds. So that's a very good fast adiabatic CZ gate inside one module in the quantum processor. We use this technique for so many different studies. I'm not going to go through all of that, such as the effect of non-adiabatic errors, spectator-associated errors, because we have more than 2 qubits here. What would be the structure of the pulse, if it's rectangular, if it's a smooth pulse, the synchronization scheme, the bandwidths of the electronics, how they can actually play a role. I'm going to show you 2 other results from this research. The other one is actually about the cross-resonance C0 gate. That's actually between the 2 different modules. So this is a long-range entanglement, and we implemented that using microwave drives that are added to the quantum dot potential. We're able to gain fidelity more than 98% and a gate time of 324 nanoseconds. And the other test that we did was on the low-frequency quasi-static charge noise, which is an important charge noise that can decohere the qubit in these processors. We studied that, and we showed that for the current state of modern electronics, which sit at the left-hand side of this graph for the strength of the noise, the fidelity is not changing. So that's a good point showing that the charge noise is not going to degrade our fidelity. The leakage error is the main source of infidelity. Again, I encourage you to read through that. There's a lot of details in that, a lot of math that we covered. And the other research direction that we work on in my group is about the interaction of quantum light and disorder. We so far talked a lot about the quantum resources and how it can help us, such as superposition, entanglement. It can help increase the sensitivity. For example, in the LIGO detectors, using a squeezed light, we're able to actually improve the sensing. It can be used for the quantum key distribution in satellite to ground links. It can be used in quantum computing, so many different areas, so many different applications. When we look at the nature around us, we see randomness a lot in nature as well as in technologies. So when quantum excitation is going to be used in different natural platforms, such as atmospheric systems, turbulent atmospheric systems, biological tissues, suspensions, optical powders, optical fibers, powders, and everything, then this randomness is going to interact with the quantum light. And very often it can degrade or alter the non-classical features. So one solution is to actually avoid interacting with randomness, but the other solution is actually using that or using the signatures that survive this randomness and what we call multiple scattering processes for different applications. I'm going to talk about one of those signatures that's happening in random structures, and then I'm going to tell you how it actually changes when we have quantum excitations. That phenomena, one of the signatures of multiple scattering, is coherent backscattering phenomena. When we have a coherent source, such as a laser, and it interacts with a random structure, such as powder, the light would get scattered. It goes in all directions, and when we look at a backscattering plane, we would see a lot of speckle patterns, constructive and destructive interference. But if we look at many different realizations of this randomness, we would be able to see that because of the constructive interference between time reverse path, there would be an enhancement in the exact backscattering direction. That's called coherent backscattering phenomena. We studied that for the classical wave. We do that with the scalar wave analysis. We modeled the structure. We solved the general Liebman-Schrödinger equation, which is a scalar integral equation, and we did a post-processing to find this effect. This is a collection of discrete point-like scatterers that we use for this scalar wave analysis. This is the mathematical details, the integral, Liebman-Schrödinger integral equation that we solved. I'm going to skip the mathematical details. The important point is that we finished with some coupled equations that we need to solve. We solve these coupled equations when we find the scattering fields at the backscattering plane. That's the speckle pattern that I told you about. So this is a publication that we had in 2022 about this work. So I'm going to show you two of those results for two different realizations of the random media. Both of these results are very much random. That's a constructive destructive interference pattern of light for this structure of disordered media. And in the next step, we did a statistical averaging. We generated so many of these realizations, and we look at the statistical behavior of this phenomena. I'm going to show you a little animation of showing how different realizations, initially being random, when they add up, they're going to show the coherent backscattering effect. So this is the animation as we add up. So these speckles are getting add up in this animation. You would be able to see that the signatures of this enhancement, that's a weak localization of light, a manifestation of weak localization of light, showing up. The left-hand side peak is the coherent backscattering peak. And it is showing up by taking an average. So this is a normalized ensemble average scattering intensity. The right-hand side peak is something different. And this is the that average for 10,000 simulations. And it matches very well with the theoretical model that was developed for a slab with a finite width. Using this platform, we use that for so many different studies. One of the important studies about the density and sample size. If you have a random structure and the density is a very important parameter. If we increase the density, we would be able to see that the coherent backscattering peaks all on the left-hand side are getting broader, which means that it can be used as a tool to actually detect the density of the randomness using light. We also did study on the absolute number of particles and sample size. These are sparse, finite structures, so the absolute number of particles and sample size also play a role. Next, we moved that to the full vectorial analysis, which means solving the Maxwell's equations. This is computationally heavy, so we needed to use GPU for doing that. The graphs are showing different number of realizations as we do the averaging, ensemble averaging. And for 2,500 particles, 2,000 simulations, we were able to see in a full vectorial format as well the signatures of coherent backscattering. That's the peak on the left-hand side, which makes it possible for us to do the polarization analysis. Next, we thought about the quantum light. What happens when we have quantum light interacting with the disorder? So if I remove the classical light, I replace that with the quantum light, the light that has non-classical features, what would I be able to see? And we showed that we would be able to see a quantum version of the coherent backscattering effect, which is the coherent two-photon backscattering. We call that coherent two-photon backscattering effect. This is the setup. So we have two-photon excitation. They're actually illuminating a random sample. We go to the far-field domain. We'll look at the signal at the detector as well as the coincidence counting circuitry. And we studied for two-photon excitation states in this form. The first version is the maximally entangled state, and the second one is a fully mixed counterpart. So this is a coherent superposition. This is the statistical mixture, which gives us a chance to see the effect of the entanglement as opposed to not having entanglement for this signature of multiple scattering. We investigated the coherent backscattering for the two-photon, the angular quantum correlations, and statistical properties of speckle patterns. First, we studied the few particles. Instead of having a lot of particles in a random structure, we just use a few particles, 2, 3, 4 particles in different arrangements. And we looked at the quantum correlation, that's the mathematical formula there. And what it shows, what does this quantum correlation mean, is actually showing how likely it is for the two photons to show up together at the same spot at the same angle. For the entangled states and fully mixed state, for both of these, we're able to see constructive and destructive interference, but the contrast of that is higher for entangled state. And there is a reason for that. That's because of the interference between the two photon amplitudes between the pairs. Next, we move that to a random structure. For the random structure, we looked at different scenarios. We have the entangled state, a fully mixed state, a classical state, all of those possibilities to look at the effect of the ensemble average two-photon current. Two-photon current is the coincidence counting of the photons. And we were able to see, these are 4 graphs for 4 different dimensionality of entanglement. M equals to 10 is a dimensionality 10 of entanglement. For all of these cases, we were able to see the signatures of enhancement, that constructive interference between time reverse path. And that's a quantum version of the coherent backscattering. There are a lot of details in these graphs. One of the conclusions is that multiple scattering actually dissolves the signatures of superposition. If you try to follow those colors, you see that the signatures of superposition at those specific points would get dissolved. But still, it is present. I mean, still the peak is present, but the nature of the superposition, whether it's coherent or statistical mixture, is not present. The other study that we did was on the ensemble average angular quantum correlation. So this is the graphs for the separation angles, different separation angles of the photons. And the conclusion is that, as I said, the quantum correlation basically says how likely it is for the two photons to show up at the same spot. It doesn't show any peak in contrast to the two-photon current. It's actually pretty much flat. In some points, it actually shows a dip. And for the entangled cases, those blue curves, for small separation angles, actually smaller than the speckled correlation angle, we would be able to see that the interference between the two photon amplitudes increases the correlation. We're able to do some analytical derivations in our paper. This is our paper that we just published in 2026, very recently. I encourage you to read that if you're interested. We're able to do mathematical derivations for the quantum correlation and find a formula for that. And that formula depends on M, which was the dimensionality of entanglement. So now this is a tool. It can be used as a tool to measure the dimensionality of entanglement in the quantum light, if you know that it's pure, which is not an easy task to accomplish. But doing these measurements and doing statistical averaging is much easier. Okay, the last piece of data that I would like to show you is about the effect of the disorder density. Talked about the classical version of this effect and how disorder is playing a role. We did a similar analysis in the structure. We increased the number of the particles. And as you increase the number of particles, the density goes high if the volume is fixed. And we were able to see that, yes, the coherent two-photon backscattering on the right-hand side, or actually the peak is much more broad compared to the left-hand side. That's because the mean free path length decreases in the structure. These are some of the results that were presented in that paper. There are so many other results that we discussed. If you're interested, I would be happy to talk with you about that. And with that, I would like to summarize what we talked about. We discussed the emergence of the quantum physics and basic concepts of quantum information science. We talked about the landscape of quantum technologies, the modern architecture, hardware, the importance of having a comprehensive layered ecosystem of technologies. We talked about the research in my group, which is on quantum optics and quantum information science, quantum dot spin systems, and quantum light and disorder. And I would like to thank everybody again for the time for joining us today, and I would be happy to answer any questions that you might have.
Okay, could Could you go back to the slides where you were showing the statistical averaging, please?
The animation.
Now go forward about 4 slides to the one where there was a maximum, one more after this, that one. I take it that the upper right, the upper left-hand corner there, where there's a very large gap between the entangled and the fully mixed state, that the delta theta is the phase angle between the two.
Delta theta is the physical separation angle between the photon pairs.
Okay.
So how they are spread physically in the space.
Okay, meaning that an angle different than coming straight back at the emitter.
No, this is for the source.
Oh,
so
for
each
the
of those source. So if I go back here, so this is dimensionality of 2.
2.
M equals to 2. So that shows the separation angle between the photon twins in the space as they are illuminating the structure.
Okay, so for small angles, it looks like the smaller the angle is, the more separation you get.
The more separation, yes.
Okay. Now if you could jump to the randomness part, where it disordered density. Recently there's been, recently there's been a number of papers that I've seen in different places trying to take an information theoretic approach to like the entropy of entangled systems.
Mm-hmm.
Is this perhaps, can you make any conclusion about what happens to the entropy of the information content of the scatter here based on increasing the density?
Based on increasing the density, what I can comment on is actually the amount of information that can be extracted. So Fisher information, the amount of the Fisher information can be compared with the classical counterpart, and that it's higher than the classical counterpart of that. So if you mean by that okay, one of the objectives of using this phenomena can be to actually use it as a tool for measuring the density by looking at the widths of this. So if it's been used as a tool, then the amount of information that you extract is important. And there have been some recent work showing that the amount of the Fisher information that can be extracted with this measurement would be higher than the classical counterparts.
Okay, so you can use this as a filter.
I would say it is more like a measurement tool.
A measurement tool that would differentially have higher responses if somebody imposed a signal on a random background at a higher density versus lower density. You would get a higher response rate from the filter as opposed to a lower response. That's my question.
Okay.
Can you conclude that from this?
Okay, so maybe we can ask the question again.
Okay.
Maybe we can discuss that further, but.
Okay, well we can take it offline, but
okay.
It looks like the more particles
Mm-hmm.
that you are scattering, then or the more distinct states there are that are scattered in the space, the higher the difference is between the information carried by the entangled pure state and the classical states.
Yeah, but we need to be careful about what do we mean by the number of particles. For example, these numbers that are shown here are the actual number of the physical point-like scatterers that are used for multiple scattering process. So in that sense, because the multiple scattering is also an operation, it's just that it's a very complex random operation that basically moves the photons in all the directions and changing all those amplitudes. So it is an operation, but it's a very complex one. So this number, I would like to highlight that it is different than the number of the photons that we illuminating.
It's actually the number of scattering of emitters that are scattering different.
It is actually yes, it is, but I wouldn't call it much like emitters. Because emitters would mean that you're actually generating that and emit that. But these are basically point-like scatterers that the light, through the interaction, would get scattered to different directions, depending on the property of that. So for example, in the full vectorial analysis that I showed you for the classical case, we actually increased the size. So those are disjoint spherical particles, like the particles that you can have in the lab, like a powder, to get simulated, that the light would get scattered off. So that's the multi-sphere Mie problem in the Maxwell solution, in the full vectorial.
For this in like detecting stealth aircraft, where you have something that is very hard to detect, but because you have the right scattering angle, it will enhance it much differentially from what it would normally be if you didn't know that angle.
Oh, okay. So that comes to the engineering of the scattering profile of the structure. That can be for certain specific structures like particles. But I would like to highlight here that this is coming through the averaging. So as you notice that we did 10,000 simulations of this randomness, which sometimes we can do it in time. For example, if you have a suspension and it's constantly evolving in time, you can constantly capture the data in the detector, which is something that we are simulating by changing the realization. So if it is a one-time process or if it is statistical averaging, there's a little bit of a distinction there. But the point about the coherent backscattering is that it is always because of the constructive interference between time reverse path in that multi-scattering process between the spheres. It's always going to show a peak at the exact backscattering direction, unless you apply like a magnetic field or something to break that time reversal symmetry of that structure, or time varying media or a magnetic field. But as long as it's not there, fundamentally the physics says that because of constructive interference, you should be able to get enhancement. And the theoretical ideal case is a factor of 2 to 1 for the classical intensity, ratio of 2 to 1. But in the experiment, it's less than that. And that comes because of the fundamental physics.
All right, thank you.
Cool.
Yeah, I had a quick question about the multiple architectures that you showed. Are there performance characteristics yet to evaluate them against each other, such as performance of initial capital investment versus computing processing versus energy use versus footprint? Different ways to compare those different types of architectures.
Yeah, that's a very good question. And I think the answer to that is yes and no, because it's very much evolving. There are a lot of rapid changes. So there are some metrics that, in terms of, for example, the depth of the circuit that can be simulated before the system starts to decohere, the clock rate that's applied, the number of the operations per second that can be applied. All of those are important factors, but it's not that you would be able to find all of those numbers for all of those platforms to compare them, because this is really evolving every single day. A different idea, different platforms. For example, look at the IBM, you would see that they're changing the structure, even the hardware layout of the structure, to change the number of the nearest neighbor qubits for the connectivity. So many factors are changing that I would say that it's not yet to have like so fixed universal parameters to know for all of these platforms to compare with, but they are competing in terms of like the fidelity of the operation that they have, how much time it takes for implement a certain algorithm, like the random sampling in the output compared to classical cases. So there are so many examples, but not something as universal as you mentioned.
Are there at least benchmark applications that you could compare the different platforms against the same problem space?
The platform, a lot of basically quantum algorithms, especially the ones that are more known, let's put it that way, are used in different platforms. So quantum error correction is also another thing. There are some benchmarks. But I'm not sure if I know off the top of my head like the specifics of those benchmarks to tell you, and it's the fact that they are present, the comparison are present in all the different platforms.
Well, it sounds like maybe each of the architectures is trying to solve a more specific problem as opposed to all of them trying to solve the same problem. So they're kind of focused on different things.
There are some parts that they actually overlap a lot. So improving the gate fidelity is something that's fundamental that needs to be done. Getting as closer as possible to 100% fidelity for any gate, that's something that all of them are competing against each other. And you can look at the fidelity of the IBM transmon, and you can look at the fidelity of the trapped ion and see how much higher that is. And you can compare it with the neutral atom. That's something that's very commonly, you can find it. If they publish that, they can find that. So the connectivity, the scalability, how much they can increase, how much they can increase the size of the quantum circuit that involves certain number of the qubit on the chip, and they will still be able to execute that. So that's something. The coherence time is something they are all trying to increase the coherence time consistently. So that's something that you can compare between the platform, but again, you need to be careful about the gate time for each of those operations too. So trapped ions have a longer coherence time, but the gate is also slow. So there are some specific parameters that are pretty much consistent and universal, such as gate fidelity, coherence time, connectivity, quantum error correction. That's consistent in all of the platforms, and you can certainly compare that between the trapped ion, for example, and a neutral atom. You can compare it with the superconducting.
Dr. on slides 19 and 23, you mentioned how qubits are susceptible to noise. Does this noise originate from the photoacoustic effect of photons hitting metamaterials and causing heat and expansion, or where does this noise originate from?
You mentioned 19 and...
I have a related question to that, which is, what's the source of the noise? And it seems like they should be trying to focus on eliminating the noise in the first place.
You mentioned slide 19 and 21?
19 and 23. 19 was the first slide you mentioned that noise is...
Okay. So the question, sorry, can you repeat the question?
Yeah, no problem. I just wanted to ask, where does this noise originate from? Is it from the photoacoustic effect of photons hitting metamaterials and causing heat and expansion, or is there another source of this noise?
So each of those platforms, the noise can appear differently. So for example, thermal fluctuations that can happen. Absorption of 1 quanta of photon, absorption unit of thermal energy, all of that can change. And so for example, if it is sitting inside a trapped ions, if there are fluctuations in the trap. In the semiconductor spin systems, they can be charge noise. These are electrically controlled gate-defined quantum dots. So the microwave pulse is electrically applied to the heterostructure, silicon-silicon germanium heterostructure. So there's a charge noise, natural fluctuations that happen, as well as the defects inside the semiconductor that can induce the decoherence. So multiple different noise sources, and those are hardware specific.
Thank you.
You're welcome.
Any questions?
Sorry, this is my first introduction to the quantum technology. I thought I would come and try to learn something here, but I'm trying to relate it to what I did have experience with in the past, which was the use of quantum dots for fluorescence applications for sensors and the like. And I'm trying to understand if these quantum dots are that same type of semiconductor that absorbs and re-emits, or if it's a completely different technology, because The quantum dots I worked with were collections of 50 to 100 to 100,000 atoms that absorbed light and re-emitted it at longer wavelengths. And I wasn't sure whether some of that was applicable to the type of computing, whether you're using variations of those dots that have been refined or if it's a completely different technology.
It is not a completely different technology, but there are differences. So it is a quantum dot in the sense that there's a confinement, so the electron is getting trapped inside the potential of a quantum dot, which is electrically controlled. But there are differences. So these are CMOS manufactured. So this silicon germanium heterostructure, and when the electron gas is built inside the structure, with the electrodes on top, we would be able to change the chemical potential and trap an electron inside. But there are different kind of the quantum dots. For example, those are that are naturally grown. So those are not in this fashion. They
were
cannot
spherical. They were spherical dots
Yeah.
that were just
So-
dispersed in a.
So basically, in terms of when you look at that, in terms of the structure, they also look different. So physically here, this is a heterostructure multi-layer system that the gate voltage is inducing a quantum dot in the system. But those grown self-assembled quantum dot systems, those are grown as especially being a quantum dot, so that but it can be used for different applications. It can be used for lasers. It can be used for sensing, for emitting a photon. So
But
it's
they don't have the same type of control that you have with this.
Exactly. So this makes it possible to be able to actually have a processor, quantum processor, that I can control what's happening to the electron inside that, so that I can manipulate the qubit.
Thank you.
You're welcome.
Hey, Dr. X, is it okay to take one more question?
Yeah.
Okay.
I have another, but I want to make sure that everyone else has had a chance.
I think you're good to go.
Looking at this particular slide, where you said it takes 105 physical qubits to make one error-corrected logical qubit. When you compare that ratio to, like digital computers, the ratio of extra bits that you're adding there is much, much lower compared to the data bits than this. Now, I recently read something where a group in Germany has come up with a system that uses 4 physical qubits to make one logical error-corrected qubit. And I'm wondering if is that getting close to the limit, or are we ever going to see the types of ratios for error correction in quantum systems that we see in normal digital systems?
So in the classical computing, we also do, for example, repetition codes or Hamming codes for protecting the data. But the ratios can be different because we're talking about the different platforms, different sort of the correction of the data. And qubits are very susceptible because it's not just 0, 1. It's basically everywhere on that block sphere. So the protection of the data so that we would have a meaningful high-performance quantum computing, it's a different story than keeping 0 being 0, binary 0 being 0, and binary 1 being 1. So that's the part that the huge difference shows up. And you can see that in the surface code, for example, distance 7 from the Google Quantum AI, they had to use so many physical qubits for that. But this is, well, I just want to highlight that this is one example. These are surface codes. So the data qubits and the measurement qubits, or measure qubits, as well as the extra qubits here, these are leakage removal qubits, they are laid out in on a surface. But that's not the only solution. There are so many different solutions. Currently there's a lot of studies on having lower number of physical qubits so that we would be able to actually get to implement complex problems faster with the hardware that we have. Topological solutions, so that using the topology instead of using a surface, to higher topologies to have one logical qubit for much lower number of physical qubits. That's one of the solutions. The other solutions are looking at the low density parity check codes that's also been discussed by some groups that it would need much less number of physical qubits, which would then eventually make it possible to have certain algorithms implemented or certain quantum computing process implemented sooner with the system that we have. So Cepher code is just one example.
Dr. Estakri, thank you very much.
Thank you.
Wow.
Thank you. It was great to meet you.
Wow. Thank you very much for sharing your expertise, your
Thank you very
research, and sharing with all of us. It's very much appreciated.
Thank you very much
And
for having me.
as our token of appreciation from the ACM, some coffee to help keep you
Okay.
awake to do all this research and
Okay.
keep it going.
Okay,
Thanks a lot.
That's what I would do. Okay, thank
Great.
you very much.
Yes,
Thanks
thank
for
you.
inviting me.
And thanks for everybody for engaging conversations.